So the problem is, up to here, we haven't talked about differential equations yet, right? Now let's start solving some differential equations. I'm going to go through a procedure of solving one of the simplest differential equations, and you're going to find out that there is just a little bit of modification I need to do on this to solve a real differential equation. The only difference is that the form of the energy is a little bit different. And the basis functions also has to be modified according to whatever boundary condition the differential equation is going to have. So let's solve the Poisson's equation. The Poisson's equation is the second derivative of u plus f is equal to 0. And let's have u0 equal to u1 equal to 0. So these are the boundary conditions. So first of all, what does this boundary condition do to our finite element space? So I mean, what does it? If we still use the piecewise linear and continuous functions, what is changed by the boundary condition?
It removes the last half of basis.
Yes, it actually removes two basis functions. The blue basis function no longer exists. The red basis function no longer exists, right? Because if they exist, the solution would no longer satisfy the boundary condition. Now, a question for you. What if I get a non-zero boundary condition? What if u is equal to 1 at the end? At this end. Yeah, it fixes the parameter on this basis function. It basically fixes a0, right? So you still remove a0 from the unknowns, but then you still have to keep a0 within these equations. So, so in order, let's say, for us to derive a more general form, so let's actually keep all these 4 basis functions or n+1 basis functions into the picture, right? Into the derivation. But at the very end, we are just going to either set 2 of these parameters to 0 or to some known value. All right, so let's still keep all of these basis functions in the derivation. So we already analyzed last time that this problem is equivalent to a minimization of energy problem. We are going to be minimizing the integral from 0 to 1 of what kind of energy? Anybody remember?
Potential.
So F times U, and that's like the gravitational energy, right? Actually, remember, like there is a minus sign on that, right? Gravitational energy. E squared U dx. Yeah, there is a half.
It's the kinetic energy form.
There is no kinetic energy. There is gravitational energy and the elastic energy. And the elastic energy is proportional to this guy. Right? That's the elongation of the string while pressed by this distributed force F. All right. So here is the minimization. And if you want to use finite elements, you need to be able to derive from the equation. I mean, if you know the equation, derive from the equation to an energy minimization form, or the intermediate, which is the weak form. All right. So now you minimize this, and again decompose that into a summation, and goes from 1 to n, integration xn minus 1 xn. Right. We should now be familiar to this. F times what? The summation of how many terms in the expansion, right? We are expanding u equal to summation of I equals 1. 0 to n, ai of phi. Again, we use the same kind of basis functions. How many terms is in this u after I split this integral? Just 2, because in every element here, I'm integrating over an element, right? How many of these basis functions are non-zero? 2. Which 2? Yes. Phi n and phi n plus 1. Right? Only these 2 terms are non-zero. Okay?
Are we going from n minus 1 to n? This is a natural term for backwards integration. You're
So-
going from n minus 1.
So, pardon?
You're going from n minus 1 to n, so rather
Yes.
than n plus 1.
This is n plus 1 or minus
It's n minus
1?
1.
Oh, okay, sorry.
Yeah, this is n minus 1. So maybe I should switch them. Let's. So let me actually use a different color for the n plus 1s. Oh, for the n's. Okay, and then comes the quadratic term, right? The quadratic terms. Again, we have a n minus 1 times here. Now, the phi n minus 1 dx plus the green. The derivatives are new, right? But we are going to see the derivatives actually makes the math easier rather than harder. All right. So now let's expand them. Again, starting from the quadratic terms. Why not? So the quadratic terms are, let's follow out the summation. The quadratic terms, we have a n minus 1 squares times something, right? Plus summation of a n squared times something, plus summation of a n minus 1 times something, plus then it comes the linear terms a n times something and a n minus 1 times something, right? Now, okay, so again, what is this? What is the term that is proportional to a n minus 1? Half of dn dx squared integrated, right? Let's write it. So a half of derivative of phi minus 1 squared, and here half of d phi n dx squared, and here, well, here I don't think I have half anymore, right? Okay, so it's a d phi n dx, d phi n minus 1 dx, right? Okay, let me again look at the form or the shape of these basis functions. Let me still write. The first one is this guy. The first one is this guy. It's called phi 0. Phi 0 actually stays 0 over here. And next one is phi 1. Okay, and next one, let's use phi 2. And I'm using this again. And I have the green, which is phi 2, or phi 3. So, what is this integral? What is d phi n minus 1 over dx in the element n? So, first element, second element, third element. Sorry?
Minus 1.
So it's negative, right? So because for each element, we are looking at the basis function that is peaks at the left node. So it goes down. The derivative is negative, but it's negative what? It's negative what again? 0 over 1/3. Phi 0 always. I mean, all of these peaks at exactly 1, right? That's kind of the definition of that's our choice, right? Our choice of the basis functions is the most convenient. Okay?
Sorry,
Always
I was
except 1, right?
-1 divided by the width.
Yes, it's actually 1 divided by the width. That's -1, right? That's the size of this derivative, and it's a constant. So how is that squared integrated over that element? It's always.